Now let's take a look at the null space of a matrix A. So we're back in matrix world here. This is also referred to as the kernel of A sometimes, although I'll generally refer to it as the null space. And it consists of a special set of values x that outputs the zero vector specifically. So it consists of all the values x, all the vectors, such that a times x is equal to the zero vector. And again, here x is an element of the reals. No, it's not. And here x is an element of Rn. And we denote it by n of A. And as it turns out, the null space is a subspace of Rn. This is theorem 4 in your text. I won't really draw a whole lot out of it, but just to recognize that the null space does have the properties of being a vector space, so it's a subspace of Rn. And let's look at an example of how we can determine this one. So we want to go ahead and describe the null space of A, given that A is going to be a 3x4 matrix. 1, 2, 1, 1, 1, 2, 3, 5, 4, 1, 4, negative 1. So there's our matrix A. And again, what we need to have is must solve the system A times a vector x equals the zero vector. So because we're solving a system where this is equal to 0, essentially we're solving the homogeneous equation that comes from this particular matrix. So we want the output or the solutions to be the zero vector, which means that we're going to look at 1, 2, 1, 1, 1, 2, 3, 5, 4, 1, 4, negative 1, and the zero vector on the other side of the augmented matrix. And then we just go ahead and solve. So this is a pretty straightforward process. We can go ahead and plug it into our octave and row ref this, solve for our specific variables like we've been doing. So x1 equals negative 2x3 minus 3x4. x2 is going to be equal to minus x cubed plus 2x4. x3 is going to be a free variable or independent, and x4 is also going to be an independent variable here. So I've done all the detailed work there to get to that solution set, which is kind of the important part. Now that we've got that, we can continue our description. So we'll go ahead and write in vector form now. And we have the following: x1, x2, x3, x4. So here's our vectors. And this is going to be equal to x3 times minus 2, minus 2, 1, 0, and x4, so plus x4, minus 3, 2, 0, 1. So there is our description of the set of all vectors here. So it has to be a linear combination of these two vectors if it's going to output the zero vector. So we can then describe our null space in the following way. So it's the set of all vectors x such that x is equal to x3 times our vector minus 2, minus 2, 1, 0. This is just, again, our formal notation, plus x4 times minus 3, 2, 0, 1. Where x3 and x4 are elements of the real numbers, And we'll throw another bracket on the back of that, and that becomes our complete description for the null space of this particular matrix. So see if you can give that a try on this example and see how it goes.